So we saw at the end of the last page that when we took a discrete probability distribution and we started taking the sampling distribution of sample means, we ended up getting something that looked like a normal curve for discrete things. So that leads us to the central limit theorem. The central limit theorem describes the shape of the sampling distribution of the sample mean. So it's exactly the theorem that we want to look at for the sampling distribution of the sample mean. If the population is normally distributed, then the sampling distribution, x bar, is also normally distributed for any sample size n, right? So if you take a normal distribution and you just start taking the sampling distribution for any size n, you will end up getting another normal distribution. But let's say that you have a population distribution, which is not normal. So it's skewed to the left, skewed to the right. It might be bimodal, it might be multimodal, it might just be whatever your data set is. The central limit theorem kind of takes care of that for us. So if n is greater than or equal to 30, right? So if our sample sizes that we're taking means of are at least 30 different numbers, and we take all different combinations of 30, then the sampling distribution of the sample mean is going to be approximately normal with mean, variance, and standard error given by, again, the mean of the sampling distribution is equal to the population mean. The variance of the sampling distribution is equal to the variance of the population divided by the number n, which are the sample sizes that you're taking. And then the standard deviation of the sampling distribution of the sample mean, which is called the sampling or standard error, is going to be the standard deviation divided by square root n. Now, the larger the n is, so the more values you're taking for these sampling sample means, the better the approximation will be. So the more normal it would look. And also the closer that the population was to already being normal, the better the approximation will be. So essentially, if you're taking large sample sizes, you're essentially forcing your distribution to be normal. And if your distribution was fairly close to being normal, like let's say it was off by just a little bit, then by taking the sampling distribution, you're making it more closer to being normal. If the original distribution is drastically skewed, you may have to take a sample size that is much larger than 30 to get a good approximation. Right, but here's essentially what the central limit theorem does. Let's say that we have any population distribution. It just has this random curve. Remember, that's a population distribution, so the area under this curve should all equal 1. And here's our mean. Our standard deviation sigma is this far apart. This is bimodal. It has 1, 2 different bumps here. But once you take sample sizes that are greater than or equal to 30, you can look at the distribution of the sample means, and it's going to look like a normal curve. So even though this was not a normal curve, taking sample sizes of at least 30, taking the sample distribution of the sample mean, and creating that will give you a normal distribution, and then we can do everything we did in 5.1 through 5.3 on this new distribution and give us information about this old one. Now, if we already had a normal distribution, it's going to keep it as a normal distribution. So normal distributions go to normal distributions, non-normal distributions get turned into normal distributions. All right, let's look at an example and see how this works. So for the population of farm workers in New Zealand, suppose that weekly income has a distribution that is skewed right. So it's not a normal distribution, but we know that the mean, mu, is 500 New Zealand dollars. The standard deviation, sigma, is 160. And we're taking a survey of 100 farmers. So N equals 100, including the information on their weekly income. So to begin with, we want to find the mean and standard error of the sampling distribution of X bar. So to begin, we have mu sub X bar, the mean of the sampling distribution, is always going to equal just regular mu. So that gives us 500. Now the standard error is really just the population standard deviation divided by the square root of the sample size n. So that's going to be 160 divided by the square root of 100, which gives us square root of 100 is 10. So we have 160 over 10, which gives us 16. Now, one thing to notice is that 100, our n value, is greater than or equal to 30. And so central limit theorem says that this sampling distribution of the sample mean is approximately normal. And so we can start answering questions like, what is the probability that the mean weekly income of these 100 employees or workers is less than $448? So we're looking for the probability that the mean of their wages is less than 448. Now, since it's approximately normal, we can take 448 and turn it into a z-score and use our z-charts to make heads or tails of this probability. So we have z is less than 448 minus 500 over 16, which is equal to probability that z is less than negative 3.25. And if you go into your chart, the negative chart, find 3.25, negative 3.25, you end up getting 0.0006. Right, so there's a very low probability that the sample of 100 has an average that is less than 448 if the population average is 500 and the standard deviation of the population is 160. Very low probability that the average is going to be so low. Next, we want to find the probability that the mean weekly income of these 100 workers is between $480 and $520. So again, we're going to do probability that it's between 480 and 520. Since again, we just ran our distribution through the central limit theorem and our sample size was 100, we can use just our regular z-charts to calculate these probabilities. Right. Here, this 16 is the standard deviation of the sampling distribution, not the population distribution. Right. And so if you do the calculation, you end up getting that this is the probability negative 1.25 less than or equal to z, which is less than or equal to 1.25. Go into your chart, find those two values, you end up getting 0.8944 minus 0.1056. Because remember, this is really the probability that z is less than or equal to 1.25 minus the probability that z is less than or equal to negative 1.25. And once you subtract those two, you get 0.7888.